Hi, I'm Alex, and today I'll be explaining to you how caches play a role in memory hierarchy and how they are utilized by the computer in order to bring down memory access times, which typically is the slowest component of any computer we have today. So, memory hierarchy, we can pretty much think about this as an analogy to you making dinner. So, when you are making dinner, you are basically the processor and you're taking inputs such as ingredients to make dinner. Similar, a processor takes in inputs as data to perform operations and execute code. So at the very top, we have the registers, which exist in the CPU. And this, in your making dinner example, could be basically your cutting board. So you have a very finite amount of space and small amount of storage that you can currently, basically, this is exactly what you're working on. So the processor can only work on what it has in the register at the moment, and you can only work on what you have on your cutting board at the moment. So small space, but extremely fast access times in terms of accessing your register would be somewhere around sub-nanoseconds, and you accessing something on your cutting board would be somewhere very fast because it's right there in front of you. So what if you have something that you don't have currently in your register and you have something that you need to, say, like bake a cake, you need flour, you don't have it on your cutting board, where do you get it? One classic example would be go to Kroger and buy it and then bring it back to your cutting board so you can work on that as you're making dinner. In terms of how Kroger is represented in our memory hierarchy, that would be the disk. As you can imagine, Kroger is very large, similar to how your disk is, and accessing that will pretty much guarantee that whatever memory you have, data that you need would be there in your disk, similar to how flour would be at Kroger. However, as you can think about in the example, driving to Kroger to get your flour and coming back is extremely slow. So a processor accessing memory in the disk to bring it back is also really slow. And this is on the orders of several tens of milliseconds. So as you can see, it is orders of magnitude slower than just accessing something in your register. And to add on to that, we have other components in your memory hierarchy to speed things up. One example is main memory or DRAM in your computer, and in the making dinner example would be your pantry. So let's add this as main memory. So main memory is several gigabytes, and in your pantry it's much larger than your cutting board, but obviously much smaller than Kroger and much smaller than your disk. And accesses to main memory would be on the orders of maybe several hundred nanoseconds. So by no means as fast as accessing something in registers, but much faster than accessing something in your disk. Similar like Kroger, or the Kroger pantry example, if you have something that you need when you're making dinner, check if it's in your pantry. If it's not in your pantry, then you have to go to Kroger and buy it and then bring it up to when you need it. So obviously, accessing main memory much faster than going to the disk, and you can hold more information, and you can hold more ingredients in your pantry, and that helps speed things up as you have another middle layer to access before you go to the disk. So caches basically fit in between the register and the main memory. And this you can think about as your kitchen space or your countertop. So anything that you have in your main memory, you can bring it into your cache or your countertop before you start working on it in your register or your cutting board. So if you're working on your cutting board, making a sauce or something, and you realize I need salt. You don't have it in your cutting board, you can probably somewhere going to be in your cache because you brought it in from main memory, and because you brought it in from your pantry at some point earlier, you use salt, so you brought it in and you don't need it now, so it'll be sitting on your countertop for access. So accessing your cache obviously would be not as fast as pipelines as we saw before, but much faster than main memory, and obviously much faster than disk. So 20 nanoseconds is pretty average time for what we have today. So as you can see, working top to bottom as we go down, we have increasing storage space. And so registers, finite number of registers, maybe 64 words. Caches, maybe several megabytes, which is your countertop, and then your cutting board. Main memory, 4 to 16 gigabytes today is pretty common, which is your pantry. And then obviously you have the massive storage device, the disk, several terabytes, and your Kroger nearby. So as we go down, much higher storage capacities, but as we go back up, we have much faster access times. So hopefully this helps you explain what's going on. Do you have any other questions as to how this works or anything explained in lecture?
In lecture, the professor talked about something called LRU. Could you briefly go over that?
Yeah, sure. So LRU is one of the eviction policies that we have for the cache. So LRU stands for least recently used, and we base what we select to evict from the cache based off that. So going back to the bacon dinner example, so this is your cache. You have like a finite number of things that can fit in your cache. For example, just have 3 items. So you're baking cake, and the first thing you use is flour. Among other things, you have eggs, maybe butter. So then maybe after you use your flour, your eggs, your butter, you realize you need something like sugar. But your cache is already full, and you're trying to bring in sugar to your cache from main memory into your cache, so when you use sugar later on, you have that fast access time. So what do you choose to evict? So then LRU basically operates on temporal locality, which is the principle that something that you used recently is more likely to be used in the near future than something you used a long time ago. So basically, the more recently you used it, the more likely you're to use it in the future, and anything used far behind in the past, you can evict that because you're less likely to use that. So in this case, we first use flour, then we use eggs, then we use butter, and now you need to make room for sugar. So based off LRU, we select that flour is something that we used far back, and eggs and butter we used more recently. So evict flour and make space to put in your sugar into your cache. Similarly, if you have run out of room on your countertop in your kitchen and you want to bring in sugar, you free up flour because you used that the longest time ago, and you're less likely to use it than eggs and butter. So you remove flour and you place sugar in a spot. So that's how the LRU basically selects what blocks that they have for eviction from the cache. So hopefully that helps you explain caches better and LRU. Do you have any? Hopefully you have any questions, because unfortunately we've run out of time today. But happy Thanksgiving and happy caching.